Hi, everyone. We are going to have our keynote talk. I'm so delighted to introduce Professor Cameron McIntyre. Professor McIntyre received his PhD in biomedical engineering from Case Western University, and then he performed his postdoc training at Johns Hopkins University and Emory University, where he started studying deep brain stimulation. Then he started his lab at the Cleveland Clinic Foundation, and then moved to Case Western University to create the Case Neuromodulation Center. Cameron is currently a professor in the School of Medicine, Department of Biomedical Engineering, and the fundamental goal of the research program in his lab is to use knowledge on the therapeutic mechanism of DBS to better engineer the next generation of DBS technology. And it is to be noted that McIntyre Lab invented the Guide DBS clinical programming system, which was commercialized by spin-off company and then acquired by Boston Scientific Neuromodulation Corporation, and now has CE mark, which stands for European Conformity Approval in Europe. Thank you so much, Cameron. We're so happy to have you here. I'm going to focus on your screen, and you can go ahead and present yourself.
Okay, great. So
I just focused on, sorry. Let me unfocus. I focused on, there is, what is this? I cannot see yours.
Okay.
So, okay, now I see. Okay, so you can go your slides and
Yep, okay.
Yep.
So, yeah, thanks for the opportunity to talk with you guys. This is a very interesting conference and a great forum, and I'm glad we have the opportunity to do it under these very strange world times that we're in. So, so I'm going to talk about, I guess you'd say a burgeoning field of deep brain stimulation that's been developing over the last, I don't know, maybe almost 10 years now. And it's been coined this term kind of connectomic deep brain stimulation. So in the intro talk, you heard a little bit about the concept of deep brain stimulation, and it's a pretty powerful clinical tool now evolving. So I guess before I get going on various financial conflicts of interest, my laboratory works in, to develop clinical technologies. And so that leads to associations with private industry. So,
Cameron, so sorry, excuse me. Can you press on the hide on the bottom of your presentation?
Yes.
Yeah, perfect. Thank you so much.
Okay. So clinical deep brain stimulation has been very, very successful in the treatment of Parkinson's disease, and that's really its main bread and butter. That's how the therapy really got started, and where almost all of the clinical activity really focuses on. Worldwide, probably somewhere between 150 and 200,000 Parkinson's patients have been implanted with DBS systems. And then there's also other applications that have FDA approval, and in some ways could be considered standard of care, but really only in Parkinson's disease would deep brain stimulation be considered real standard of care. And those other indications have been in other movement disorders, so essential tremor, dystonia. There's also FDA approved deep brain stimulation devices for the treatment of epilepsy. It does have a humanitarian device exemption for the treatment of obsessive compulsive disorder. But a lot of the research side of deep brain stimulation over the last, decade has tried to find new opportunities, new clinical indications that could possibly use this, let's call it a platform tool. And two of those that are, of great interest are Alzheimer's disease and depression, because those are two gigantic clinical markets that have a sizable number of patients that they would consider treatment refractory. So there's just no other option for them once they progress to a certain point in the disorder. So deep brain stimulation technology is pretty simple. Really, this is technology adapted from the spinal cord stimulation world or the cardiac pacing world, and it's primarily broken up with three major pieces of the tool. So there's the implanted pulse generator that is effectively about 80% of it is a battery, and the other 20% is electronics connected to a electrode that is permanently implanted in the brain. That device, this fully implanted stimulation device, is controlled by an external programmer that the clinician, the neurologist, uses to turn the stimulator on and off and adjust the stimulation parameter settings delivered through these individual electrode contacts. And then the patient has a device that they can use to basically turn the stimulator on and off. Most patients, especially Parkinson's patients, just leave their stimulators on 24 hours a day, 7 days a week. So deep brain stimulation is, what we call it a last resort therapy. For example, someone with Parkinson's disease will have been treated with pharmacology for many years before they become a candidate for deep brain stimulation. Or in the context of neuropsychiatric disorders, once again, they will have failed several other things: pharmacology, electroconvulsive therapy, cognitive behavioral therapy, before they would have become a candidate for deep brain stimulation. But once the clinical team has, kind of come up with, the criteria that the patient meets, for real consideration for DBS, then you would move on to sort of that phase of, meeting the neurosurgeon, learning about the approach, and deciding whether or not you would want to go forward with it. Then the actual deep brain stimulation surgery consists of, using what we call stereotactic neurosurgical techniques. So most deep brain stimulation surgeries are implanted using what's called a stereotactic frame. So a rigid kind of base is effectively attached to the skull. And then this, sort of manipulandum is what the neurosurgeon then uses to now provide. So this base provides a coordinate system that the neurosurgeon can work in. And then this device provides a way to precisely deliver, a probe into the brain. And that is augmented by commercial, FDA-approved software technologies that are designed to work in conjunction with these neurosurgical frame systems. So there are many different companies that make these things. I'm just showing two examples in these pictures just to give you an idea. But so MRI-based guidance is the standard in this field. And so you've got the patient MRI. The neurosurgeon then has to pick a target location in the brain that they want the tip of the electrode to go. Then they have to find a safe trajectory through the brain, avoiding blood vessels, sulci, ventricles, and an entry point that they're going to drill a small burr hole in the skull so that they can get their probe down to that target point. So, like I said, about 15 years ago, people really were interested in the concept of taking deep brain stimulation out of the world of movement disorders and trying to find ways to use it in the context of neuropsychiatric disorders. So to give you some background and context, before the world of deep brain stimulation, there was a similarly effective world of what they would call stereotactic ablation for the treatment of neuropsychiatric disorders. And that world basically would go in and ablate parts of the brain to treat neurological disorders. And they did that for Parkinson's by ablating what's called the globus pallidus. For neuropsychiatric disorders, they used to do what you would call a callosotomy or corpus callosum, ablations. So they would do ablations in this part of the white matter to treat all kinds of different neuropsychiatric disorders with varying levels of therapeutic benefit. But because deep brain stimulation and ablation techniques from a surgical perspective had generated pretty similar therapeutic effects, people started thinking, well, since ablation had done, some positive effects for the treatment of neuropsychiatric disorders, maybe deep brain stimulation could also do a good job treating neuropsychiatric disorders. And another area that's very popular for, treating neuropsychiatric disorders with ablation was this area called the ventral capsule, or the ventral striatum. And so another white matter territory that actually doesn't really show up on this particular picture very well. Anyway, there were ideas of targets in the brain that you might want to go to put a deep brain stimulation electrode for the treatment of neuropsychiatric disorders. And then Helen Mayberg came along, and she came at it from the perspective of a functional imaging, sort of hypothesis-driven target identification. So in the late 90s, she had been doing a lot of fMRI and PET studies. Actually, I think more PET than anything else, positron emission tomography studies. And she had identified this area where this red dot is as some kind of let's call it a processing hub for neuropsychiatric dysfunction. And so her hypothesis was, well, what if we don't ablate that area like historical neuropsychiatric neurosurgery, but what if we actually put a deep brain stimulation lead in there and activated it and see if we could make treatment refractory depression patients better. So that was the hypothesis. The first case study, or a first series of patients, was published in 2005, and it showed pretty promising results. So this is the general target location that the neurosurgeon would use, and then this is an overlay of CT artifact of where the deep brain stimulation electrode contacts ended up in an example patient. So maybe, follow this field, maybe not, but deep brain stimulation for depression then went through a gigantic, so that was the technology trigger, that kind of neuron paper from 2005. Deep brain stimulation for depression then went through a gigantic rise in hype and reached a peak of inflated expectations, I would say, in about 2008, 9 time window. 2 gigantic industry-sponsored clinical trials got underway with very little, let's say, background understanding of what we were actually doing with this technology, but there were at least a number of, open label clinical trials that have suggested, wow, we can get, really dramatic effects in the treatment of depression using deep brain stimulation technologies. Then after those trials kind of really got going, and they were, blinded controlled studies, and the studies really weren't working out all that well, let's say about 2016, 17, 18, the trials are effectively halted, and we reached the trough of disillusionment. And there was really, sort of like, the people working in this field kind of were in their own state of depression, and trying to think of, where did we go wrong? What did we go wrong? And it was about at this time, at the very peak of inflated expectations, that I was like, oh yeah, for sure, I want to work on this problem. And I, watched and was an active participant as things really fell down into this trough. And we kind of got to this point where we needed to think of how and what can we do to help push things up the slope of enlightenment to then reach the plateau of productivity. So, for example, deep brain stimulation for the treatment of Parkinson's disease is what, people will consider has reached the plateau of productivity. But deep brain stimulation for neuropsychiatric diseases is still, maybe making its way up this line here. So these are big dollar decisions, and really, the stakes are very high. Obviously, the stakes are high for the patients, but they're also very high for a company to run something like that. So to go from a first-in-man proof of concept clinical study to an FDA-approved, neuromodulation device, brain implant, you're talking about $100 million, easy to get to that point. And so for a big company, to make a decision like that, there's a lot of risk involved, and they are very much interested in mitigating risk and maximizing the probability of success. So, so this is, one of these examples of, one of these large-scale clinical trials that was halted for, a lack of, I can't remember the exact wording that they used, but effectively halted because they were not going to reach their statistical study endpoints that would be able to give them the FDA approval that they were seeking. So that then leads to this very logical question. Well, what happened in the responders? So some patients did get better, about 50% got better, and about 50% didn't. And so what was it about the responders that was working in terms of electrode location, stimulation parameters, whatnot? And what was it about the non-responders that wasn't working? Right? Was it not the right selection of patients? Was it not the right placement for the electrodes? It could have been millions of things. But with most neurosurgical interventions, the first thing that you think about is, well, where did the intervention actually end up? And if you compared the responders in these kind of blue heat maps, so these are locations of probabilities of where electrodes ended up in an atlas brain, right? So this is an MNI atlas brain. And then the heat map is showing where the probability of electrode locations were in the responders versus the non-responders. And, we did a number of different statistical analyses on these things, and it looked to us like it wasn't electrode location that was differentiating responders versus non-responders. But right about that same time, this whole concept of human connectomic, analyses based on primarily diffusion-weighted imaging data, so DTA data or tractography analyses of diffusion-weighted imaging data, and the big financial backing of the NIH and the creation of what they called the Human Connectome Project was really getting going. So this is now, once again, 2012 to 15 kind of time window. So that, was really taking the scientific human neuroimaging world by storm. And at that same time, Helen and I were just starting to kind of think about, ideas of how we could use that kind of basic scientific foundation to help us interrogate these patients that had been implanted with deep brain stimulation systems. And so, and a huge part of that motivation was that we, based on the biophysics of how the nervous system responds to electric fields, we already knew that primarily, what you think about stimulating with deep brain stimulation electrodes are actually axons. They're biophysically sort of some of the most excitable neural elements that are going to be in the nervous system. And so we knew that we were interested in understanding how axons responded to stimulation. And we now had this new, let's call it, circuitry roadmap that was primarily based on characterizing axons and their connections within the nervous system from these kinds of diffusion-weighted imaging data sets. So then it didn't take a rocket scientist to think about, well, how can we start to integrate these things together? So, so we started combining the concepts of, sort of tractography data. So these individual streamlined trajectories of the, millions of different axons that are passing through this, sort of area of clinical interest, coupling that with finite element electric field models of the voltage distribution generated by the stimulating electrodes. And if you then know the response or the voltage distribution generated by the stimulating electrodes along the different axonal trajectories, you can then come up with models that can characterize the response of that simulated axon to the simulated electric field. And then we might have, a proxy that could give us some kind of a computational estimate of what our stimulation might be doing to different brain connections in the patient. So that was the conceptual idea. So how could we start building something like that? Well, you've got your called a tractography streamline or an axon trajectory here, this black line. And then you've got it's running by our deep brain stimulation electrode here, and we're going to be stimulating through this red contact. And you can break this tractography streamline up into many, many pieces. And in each little piece, you can effectively, provide it with Hodgkin-Huxley style membrane dynamics that can represent the sodium-potassium channels that are actually responsible for action potential, generation and propagation. And so that then gives us let's call it a biophysical representation of the axon. And you couple that then with the DBS voltage distribution that gets applied along the trajectory. And that then gives you an extracellular driving force. So if we go back here, imagine now we've got a voltage at this point and at this point and at every point of this multi-compartment cable. That extracellular voltage is going to cause current flow in and out of the neural membrane, by this external driving force. And it is then that extracellular polarization that comes from the DBS stimulus pulse that then can create the generation of an action potential. And that action potential would then propagate along the trajectory of that axon, in both directions. So you create an artificial action potential in the middle of the axon as it passes by the electrode, and then that action potential propagates in both directions off into wherever the cell body of that neuron is, as well as its axon terminals. Okay, so that then gave us a tool to try and characterize how stimulation could be tied to a neural response that we could try and quantify on a patient-specific basis. And we started calling these things pathway activation models. So here's an example patient. So here's a kind of coronal view and a sagittal view of where the electrode was implanted in that subject. Contact 3 was the therapeutic stimulation contact. We'd then create, the hundreds of thousands of axonal trajectories that kind of course through the region that is, our area of interest. You then solve for the electric field and voltage distribution generated by that stimulation. And then you pull out the individual axonal streamlines or connections that were super threshold for the generation of action potentials in response to the specific stimulation parameter settings that were used in that subject. And so here's an example of, therapeutic stimulation that actually caused this particular patient to be, effectively, cured, so to speak, from their depressive symptoms, or a stimulation just 3 millimeters away from that, so contact 3 to contact 1, that had no discernible effect on the subject behaviorally or any other way. So you can see very dramatic differences in the neural connections that are being stimulated in these two example stimulation experiments, if you will. And so that gave us then some insight that there might be something that's not necessarily about millimeters of difference in anatomical placement of the electrodes, but very differences that happen in the connectivity of what is being stimulated that could have a key effect in understanding why some patients did well in DBS for depression and other patients, were non-responders. So that first paper was looking at just one subject. The next paper, doesn't take a rocket scientist. Let's do this on 20 subjects and see, if we can find some trends. And that's what we did. So, and what we started to see now, these are heat maps of axonal pathway, sort of streamline densities during responsive stimulation versus non-responder stimulation. And you can see there was something that was different about the responders and non-responders. The responders were getting, activation of, pathways that are going up into the cingulate bundle. They were getting activation of pathways that were getting down to this ventral medial prefrontal cortex. Same thing with some of these patients who started off being non-responders, but through clinical adjustment of the stimulation parameter settings, they were able to eventually become responders as the psychiatrist kind of titrated the therapy. And you can see that their activation patterns also started to follow this very, let's call it a blueprint of connectivity that seemed to be representative of therapeutic effect. So that then gave us a blueprint to actually think about how could you prospectively, design the targeting of the electrode placement, the selection of the stimulation parameter settings, and the customization of the therapy, to the subject. And so through, lots of retrospective analyses and some, I'd say logical thinking about neuroanatomy, we started to realize that there was this sort of unique thing about what they called the subcolossal cingulate, or this generic target that was being used for the treatment of depression. And that wasn't really the gray matter, so to speak, that we cared so much about. It was this confluence of different white matter pathways in a unique combination that could give us the therapeutic effect that seemed to be representative of, predictive of, subjects that were going to respond to the therapy compared to those who might have electrodes in this area, but were not stimulating this confluence of fibers. So now you've got a computational blueprint that you can use to develop a targeting algorithm, if you will, for clinical treatment. And so that's what we started to do. So, my group is, interested in the biophysics of neurostimulation, but we're also interested in let's say the clinical development of technology that could be, kind of prototype technology for eventual, neurosurgical navigation. So there are companies, like BrainLab and Medtronic, they're going to build FDA-approved, technologies that are meant for commercial sale and whatnot, but their time course for the development of technologies is much, much slower than what an academic laboratory can do. We can build a prototype and test a hypothesis in a much, much faster time window. So that's sort of what I see as our niche. We can kind of prototype ideas that then might be helpful to these big neurosurgical navigation companies. And so that's what we started to do. So we have our own, let's call it an academic neurosurgical navigation platform. We call it StimVision. And it's, really has many of the same features that the commercial FDA-approved platforms have, but we have a lot greater creative control over adding new features and building in new technology. So we had this idea, you've got the stereotactic coordinate system that the neurosurgical frame is based upon. You can visualize where the electrode is going to go in that patient. You've got their MRI data, but then the new bell and whistle was let's add, all of this pathway information and be able to interactively visualize how, as we change the things that the neurosurgeon actually has control over, the parameters of the neurosurgical frame, how does that adjust or affect or impact our interaction with these target pathways that we care about, as opposed to historically how you would do that with just, the MRI gray white matter, sort of contrast as your guidepost. So here I'm going to walk through how that, kind of system is built up. So you start with the preoperative MRI data set, and it has these fiducial markers in it that are representative of the coordinate system of the surgical frame. You then incorporate in the patient-specific tractography data. So this is whole brain tractography that was created from, human connectome level, kind of preoperative imaging, then pre-processed, within, various software technologies, and then, loaded into here. So, all of that pre-processing had to happen way before the actual day of surgery, but you're planning ahead, to be ready for that, so that we could then take that technology and put it into the hands of the neurosurgeon on the day of the surgery, so that they could interactively plan the DBS trajectory. So in this case, Bob Gross was the neurosurgeon. He would then plan a trajectory for the placement of the deep brain stimulation electrode based on the historical concept of how you would do that with anatomical landmarks in the MRI. Then we would iteratively kind of move these numbers around to then not just put the electrode in the right general location in the anatomy, but also so that you capture these very specific pathways that we wanted to capture. So this red pathway is called forceps minor. This green pathway is called the cingulum bundle. So we knew that it was, if you get not just in that general area, but this confluence of fibers within that area in the unique neuroanatomy of the patient, that was really predictive of therapeutic effect. So how did this, kind of all work out? Well, if you use traditional anatomical targeting for subcolossal cingulate deep brain stimulation for the treatment of depression, in open label, clinical trials, they would see, approximately a 60% response rate. So at 2 years, 24 months, 24 weeks, which is 6 months, I think. Is that right? 6, 4, 24. Yeah. So they would expect to have, approximately 60% of the patients be considered responding to the therapy. So greater than 50% improvement in the clinical rating scales for depression. When they moved to the full-on FDA approved, or clinical trial for FDA approval, that response rate dropped down to 50%, and that was less than what they needed to, to have any hope of getting FDA approval for that technology. And so that trial was then halted. When we moved to then, now that, in parallel with this large clinical trial that was going on, we were also doing research trials. The Mayberg lab was doing research trials at Emory. Once again, using more of the, open label type approach, but even still, we had moved to this concept of connectomic targeting. So we were using STEM vision, or early iterations of that concept, to then do targeting in a little bit more patient-specific way. And, at that 6-month time window, we were already, up to, kind of having a better response rate. There was a hint that this might actually be a good idea. And then the most recent work where we've, actually used, more refined versions of the STEM Vision software and really integrated it with the neurosurgical workflow, the last 6 of 6 when this human brain mapping paper came out, and actually 7 of 8 now that total that have been done over the last, more recent time, there is something special about using this, let's call it more advanced targeting concept to really be able to customize the therapy to the patient. So we're making progress there, and one of the things that was became pretty obvious to us as we started working on this concept of connectomic targeting was, neurosurgical targeting is already a very complex 3D problem. And when you start throwing in, things like, all of these complicated axonal pathways and things that actually, most neurosurgeons don't really, know much about what these axonal pathways look like, because that's never been part of their training. You start throwing a lot of that really, complicated 3D information at them, and it's almost information overload. And so we started thinking about, how are we going to deal with this when, the future of neuromodulation, people think, oh, we're going to put in 10 electrodes, 20 electrodes, the combinational, kind of issue just becomes mind-boggling. There's no way you're going to process all that data. So we'd always been worried about that. And then in parallel, we also, had my university, Case Western Reserve University, had just developed, kind of new relationship with Microsoft. This is in kind of the 2015 time window. And they had this cool new idea. They called it the HoloLens. And this was this concept of a head-mounted display that would give you the simulated visualization of a hologram that you could interact with and see data in a completely, new way. And so this platform was really built off of, kind of Microsoft Kinect sensors that would map the room, a waveguide, and electronics that would then be able to reflect light back into your retina and give you the perception of a hologram, like Princess Leia talking to Luke Skywalker. Right? So this cool thing was, kind of put in my hands, and we weren't really allowed to talk about it at the time because the HoloLens wasn't even a publicly, announced thing. But I had the chance to see this technology, and after having the headset on for like 5 seconds, I was like, I know exactly what we're doing with this in neurosurgery. It was like the most, obvious thing ever to me. So, my university ended up making a really big, investment in this technology, developing a core center that's called the Interactive Commons. That's led by Mark Griswold, and it's kind of this, community center where the, faculty are encouraged to come and think about new ways of using these technologies to address, all their different research problems. So I was like the first, faculty member to just like jump in this with both feet and be like, this is the greatest thing ever. So here's an example of what this kind of technology looks like. So you wear it on your head. You're not tethered to a computer, so it's, all the processing happens. It's like you're wearing a laptop computer on your head. And then you can create simulations that can be seen by a group of people. So here's Mikkel Peterson and myself. I am controlling this holographic scene with my little iPhone interface. So the iPhone's connecting, wirelessly to the HoloLens, and then, providing feedback so that we can all see this scene in, together and really appreciate the three-dimensional features of, in this case, the brain. So, you can start loading in even more complicated data sets. So here's now, an actual MRI data set that we can interactively move around. Here are 3D anatomical nuclei of, the thalamus in yellow, or, caudate, putamen, So, the whole point is now let's start thinking about, neurosurgeons are typically thinking about, or they're planning this surgery using these 2D slices on a 2D computer screen. But what if you could start thinking about doing this kind of planning in the context of, three-dimensional rendering and interactive visualization of all of that data in a common view? So, so now we're in like 2017, 2018, and we're building these prototypes. And at the same time, we're, starting to get really encouraging results about our connectomic targeting concepts. So, it's like, every once in a while a plan comes together, like pieces start to fit and you're like, okay, I think we got something here. So now we're starting to think about, how do we integrate holographic visualization with stereotactic frame systems so that we can actually start to think about prospective neurosurgical planning with these, both advanced visualization hardware technologies, but really the more important part is the more advanced and novel, scientific data that we can give directly to the clinical team that's going to be making these really important patient-specific decisions, and millimeters matter in this game. That's, I think, maybe if I had to sum up my career over the last 20 years, that's what I've figured out. Deep brain stimulation is a super cool tool, but when you put it into an individual patient's brain, millimeters really matter. And on top of that, man, we barely know anything about these networks that we're interfacing with, especially in neuropsychiatric disorders. And so, really, innovative colleagues of mine, Samir Seth and Nader Paradian, they were working on a next generation neuromodulation, sort of platform for the treatment of depression. And so what they were thinking about was, so there's been historically two main neurosurgical targets for the treatment of neuropsychiatric disorders. So one is called stimulating in the ventral capsule, and the other has been stimulating the subcolossal cingulate. So these are two deep brain stimulation electrode targets. But we know that whatever it is those different therapies are doing, it is definitely creating modulation in cortex all over this whole prefrontal cortex area. But we don't really know anything about what that is because no one's ever been able to measure it. So in the world of epilepsy, they often put depth electrodes in many different places to try and find where the seizures are. So that's commonplace, but the world of deep brain stimulation electrodes and epilepsy electrodes really never had been brought together. And so Samir Seth and Nader Paradian put in a brain initiative, a giant brain initiative project to actually say, like DBS for depression has got potential, but we need more understanding of the science. And the only way we're going to get that is if we do, the science by combining electrophysiological recordings with deep brain stimulation to temporarily, try and interrogate these networks in patients. And so they had this new clinical trial that they were going to do where they're going to implant these DBS electrodes in both of the traditional targets and then monitor the cortical activity patterns invasively for 5 to 10 days after the surgery using SEEG, or stereo EEG is what SEEG stands for. And so I wasn't originally part of this project, but we're all friends and I knew what they were doing and we started talking about it. And these guys were two of the very first people that ever saw the original prototypes of our HoloLens system. And so we started thinking about, okay, let's join forces and actually think about, you got the most complicated neurosurgical planning, sort of issue ever. And I've got the most advanced neurosurgical navigation visualization system ever. And we've got to work together on this because, we both will benefit. So here's, this is Samir. This is the first time he ever touched the Holo SEEG platform. And so, we've got all of these SEEG leads kind of lined up off the side. He's interactively moving, one of the DBS leads into position. And he's moving the frame, but he's also interactively seeing all the different axonal connections that, he would theoretically be stimulating if he decided to put his electrode in that location. And so, so now this is like 2018 kind of time window. They haven't started their clinical trial yet. They're still trying to get all of their FDA paperwork in place and all of the infrastructure for the, you know, kind of scientific recordings that they're going to do. So now we're really starting to line up, you know, kind of form with function, and starting to think about, okay, how are we gonna make this happen? How are we gonna do, you know, real prospective neurosurgical navigation with this technology, and how we're going to apply it to this very unique clinical trial. Okay, so yeah. So then in January, right before the world, you know, kind of started changing, we all got together in Cleveland to do this very first holographic connectomic neurosurgical plan with, so it's 14 total electrode trajectories that we planned in this subject. You know, we could build the plan in our, you know, kind of holographic interface system. And then now that we've got, let's say we've built this holographic plan, that's only, you know, kind of step one of like 20 steps, you know, to actually getting these things in the brain. So once again, you know, our stuff is not FDA approved. Our stuff is not, you know, kind of, you know, it's research software. So we've got to figure out a way of how do you take that kind of research, you know, information and load it into, you know, actual FDA approved, you know, neurosurgical platform for planning. So we worked out all the file, you know, kind of transfer issues and data, you know, kind of typing issues, so that we could go from, you know, kind of this environment to the, you know, kind of environment that the neurosurgeon would normally have to do that kind of planning in. And then, you know, a real revolution that I think is going on right now in stereotactic neurosurgery is, you know, when you've got this many electrodes that you, or trajectories that you've got to deal with, it really makes sense, you know, going away from stereotactic frames and transitioning into, you know, actual robots. And this is, you know, a really interesting technology trend in neurosurgery. So, you know, these systems, you basically come up with all these trajectories, and then the robot then can, you know, kind of go through all those trajectories in a much, much faster way than can be done with adjusting the frame for every electrode. So in March, we actually, you know, I mean, the royal we, you know, went through the process of doing this first patient. And so here's the robot arm, the patient's in here. This is Samir Seth. He was a lead neurosurgeon. And then this is an O arm that takes, you know, kind of X-ray shots of, you know, the leads, so that everything can be anatomically verified. And, you know, I think this without a doubt, this is the coolest project I've ever worked on. And it was also, you know, an amazing combination of, let's call it science, engineering, and clinical medicine, you know, kind of coming together in a way that, frankly, I just found, you know, amazing. So in conclusion, you know, connectomic DBS targeting can help customize the therapy of the patient, and that can be done, you know, even with, you know, the most simple neurosurgical navigation systems now. That's now pretty much something that's integrated into, you know, those kinds of systems. I think the next generation of this technology is really going to benefit from holographic visualization and planning. It's hard to put into words. The videos are cool, but not nearly as cool as seeing it in real life. And yeah, I think that this is going to be a pretty important step forward with this kind of complex 3D system. And, you know, patient-specific modeling, I think, is a really important part of that, because, as I said before, you know, millimeters really matter in these things, and patient brains are so strangely different from subject to subject, and you never know what those nuances are until you're really in there. So I'm a big believer that, you know, doing these things in patient space is really the way to go. And I'm not a big believer in atlas consolidation approaches. Okay, so yeah, I want to thank the people that really made this work happen, Mikkel Peterson and Mark Griswold, and Helen Mayberg, Samir Seth, Nader Paradian, and the National Institutes of Health that paid for everything. So thank you. Sorry.
Thank you so much, Cameron. It was amazing. I don't know how to thank you for this great talk. So we have 10 questions, which is a lot. And
Okay, I'll try my best.
Yeah, so I think the best way, because we have a lot of questions, and the fastest, perception action way is you can see the question. Yes.
I can see like a streaming thing of, well, now it's just a whole bunch of clapping. So thank you, I appreciate that. But I can't see any questions.
Okay.
So
yeah, so I'm going to read for them
okay.
on behalf of the questioner. So.
Oh wait, now I
Oh, you
clicked
can see?
the question thing. Now I can't see that.
Okay. So I think
go all the way to the bottom or start from the top?
from the top, which is highest voted question. But I think you can leave the first one, because this is kind of from us, and we can do it in a coffee break. So please just start from the second.
Start from the second. Okay. There is quite a lot of uncertainty during track reconstruction. Do you think it is important to worry about it, or the level of detail you care about? Yeah, I think this is a huge thing. So I was one of the early people in neuromodulation or deep brain stimulation to start trying to use tractography, to do these kind of things. And over the last decade, I have come to believe that tractography is probably not good enough. And so, if you really care about this stuff, my approach was last year in Neuron, we had a paper where we actually did a different approach to reconstructing axonal pathways and using that kind of philosophy instead of traditional diffusion weighted imaging reconstructions. But I am very much in the minority. Most people are hardcore tractography is awesome, kind of philosophy. And in the case of things like giant white matter pathways that we're stimulating for neuropsychiatric disorders, it's probably good enough. We don't really know enough about the nuances of what we're trying to stimulate. And these pathways are so big and they're so robustly, reconstructible with tractography that probably not that terrible of an assumption given all the other errors in the system. I don't think that's true in other DBS, sort of applications, but for DBS or neuropsych, it's probably okay. But the jury is still out on that. I think this will be a big part of, kind of the neuroimage kinds of papers that you'll see over the next couple of years is, kind of how much should we trust it and how much should we, question it. So. Okay, next question. Did you include anadromic effects of stimulation in the models? So what we worry about, not where the signals are going, just what pathways are being stimulated. And we're not making an assumption that it's the anadromic component or the orthodromic component of the potentials that we care about, just that something about that pathway being active is what we care about. The next level of analysis that you would care about that is if you're actually trying to develop network activity models of the simulated direct activation. And I haven't really spent much time working on that kind of stuff, but there are lots of people that do. And this is where that world of functional MRI or functional imaging and network modeling really could be really awesome. And it's outside of my personal wheelhouse, but that's really the next level of kind of analysis that we probably need to start thinking about. And And I think there's a lot of opportunities there. Okay, the next question, has there been any work on the use of DBS for bioelectric medicine, i.e. using electrical stimulation, typically the PNS, to elicit immune response? I don't know much about that, but there is a big NIH initiative called SPARC. I can't remember what, SPARC is an acronym that I don't remember what it stands for. But that is all about trying to tap into the, kind of the PNS system and the autonomic nervous system and control all kinds of other things that we haven't been thinking about historically. And so I don't know anything about the immune system, so I'm definitely not the person to ask, but I think that there is a growing world trying to understand, how do we use this very generic tool to do unique and novel things in terms of controlling the nervous system. So, okay, what is the effect of different stimulation patterns on the effectivity of DBS? Okay, so that's like not just the $10,000 question, that's the $250 million question, because if you can answer that, you could start your own company and you'll be rich very quickly. So I think that we have two general, rules of thumb. High frequency stimulation typically mimics the concept of, of ablation or deletion of the activated neural elements in the nervous system. And I personally hypothesize that probably is happening via effectively you stimulate the connections at a very, very high frequency, and you basically deplete or exhaust the ability of the synaptic connections to transmit, and you create this, kind of whatever you want to call it, synaptic lesion of connectivity. Or you can stimulate with lower frequencies. So that previous concept is like 100 hertz and higher. You can pretty much, blow out a synapse after a few, 100 milliseconds and make it basically non-connected anymore. That's a generic concept. You can also stimulate at 20 hertz and have a very robust, very strongly followed signal that is, adding activity to that stimulated pathway. And that's what we do typically in the peripheral nervous system, right? You're trying to create a motor end effect, or you're trying to create some kind of neuroprosthesis. You're using lower frequency stimulation to specifically input information into the nervous system. But most things that we do are constant frequency, and nothing in the nervous system works by stimulating long-term at a constant frequency. So clearly the next step is, how do you come up with patterns of stimulation that actually mimic real neural communication? And that's a whole other world. Once again, not my personal expertise, but of great interest to the field right now, and great interest scientifically, but also great interest industrially. So, yeah. Okay. Next question: for psychiatric conditions, what kind of measure is used to classify responder non-responders? They're only looking at blueprints, as you mentioned, or the back and forth. It's like, yeah. So historically, I mean, this whole blueprint thing, connectomics, like I bet if you asked, 10 psychiatrists that work in this area, they ever even heard of this before, they'd say, no, I don't know what you're talking about. So, historically, the neuropsychiatric community uses outcome metrics like the MADRS or the Y-BOX or whatever. So these are clinical rating scales that are, based on question and answers with the subject about their mental state. Questions like, how are you feeling? And, have you thought about killing yourself? I don't know what the exact questions are, but it's things like that. That's what they're, they then score those responses and give it a rating that then tells them this is, a patient that's in this very, very severe category, or someone who's in a middle category, or someone who is, getting better, or, fine. what we presume could be a new way of thinking is, can you actually, use imaging biomarkers to classify patients? Could you use electrophysiological biomarkers, right? Their response to these stimulations, and maybe they have a special EEG response to the stimulation that tells you, you're in the right circuit, in combination with the historical measures that are the gold standard, right? So the MADRS, the Montgomery Albert rating scale, or something like that, the YBOCS, the Yale Brown obsessive compulsive disorder scale, something, there are these established gold standards that are what we always have to use as, our measure of success. But are there new measures, new biomarkers from imaging or electrophysiology that can give us, a lot more granular detail and a lot more insightful interpretation of what's actually happening, right? So that's the goal. Okay.
Cameron, sorry.
Are we out of time? Okay.
Well, yeah, and I don't know how tired you are. It would be great pleasure if we can have you in our coffee break, which is you can join us in 10 minutes probably.
Okay.
And Scott will manage that, and some question can be raised there, and it would be great if we can have you there.
Great, I'll be there.
Okay, thank you so much for your talk.
Okay,
I really
sounds
appreciate it. And I'm going to end this session, and we will have you in the next session.
Okay.
Thank
Great,
you.
Thanks. Yep. Bye.